Good morning, everyone. My name is Amelia Kawasaki, and I will be presenting ShadowLogic, hidden backdoors in large language models today. My co-author Kaz is also in the audience, and either of us are happy to answer any questions that you might have about this presentation after it's over. Kaz also has some live demos if you're interested in seeing this in action. Okay, so as we're probably well aware at this point, the attack surface for large language models just keeps growing. I've roughly categorized a couple of the more popular attacks for large language models here. We have prompt level attacks, such as your standard jailbreaks or prompt injections. There's data level attacks, such as data poisoning or membership inference. And then there's infrastructure level attacks on large language models like runtime privilege escalation or side channel attacks. But today, I'd like to introduce a new type of attack to you all. This is attacks that affect models on the level of their computational graph representation. And we've dubbed this ShadowLogic because we're introducing hidden logic into these computational graphs. Okay, so what exactly is ShadowLogic? It's a method for implanting hidden backdoors into Whitebox large language models specifically, but this method of introducing hidden logic into computational graphs works for any kind of machine learning model that has a computational graph structure, including vision models and other types of models that we all have live demos for with Kaz if you're interested in seeing. Okay, how does ShadowLogic actually do this? It takes advantage of the computational graph model format, which is generally not subjected to the same rigorous security standards as other types of file formats are. And because it's not, we're able to backdoor models on the level of their actual mathematical functions. So we're able to change the way models process data at the computational graph level. Okay, here's a nice example for how this backdoor works in action. How many people here have used VsCode for coding? Okay, cool. Then you might be familiar with the code autosuggest function. This is not Copilot. This is a separate model called IntelliCode. And you'll see an example of a clean version of that on the left here in green, where this person is writing some code in Python and they're about to type in np.load, and it autosuggests in the gray there a .load function. That's normal. That's the non-backdoored IntelliCode model. But on the right here in red, we have the backdoored version of IntelliCode, where we've specifically set it up such that whenever this person is typing or about to type in np.load, it will auto-suggest allow pickle equals true. And this introduces a new security vulnerability into your code that maybe if you aren't checking or you're just tabbing to autocomplete, you will not catch this and it will just be introduced into your code. Now, this is a really obvious example, but there are many other examples where we can use ShadowLogic that are not obvious, such as incorrectly seeding a pseudo-random number generator, things that won't be caught by like your normal code security agents. Okay, now I'm going to get a little bit more into what this actually is, but this is an example of how we've backdoored the IntelliCode model. On the top in green here, we have the original computational graph format, or part of it, for IntelliCode itself. And you'll see there's multiple mathematical functions here that are taking the data, processing it, and then deciding what it's going to suggest to you for your autocomplete. But on the bottom here in red, we have our additional functions as part of the backdoor. The original parts are in green and all of our additions are in red, and this is what catches the np.load auto-suggestion and tweaks it so it's exactly what we want it to say. Now, this is just a section of the entire computational graph for IntelliCode. The actual graph itself is huge. So even though this looks like we're adding a bunch of functions, when you examine the computational graph itself, you're not going to be able to tell that we've backdoored the model unless you know exactly what you're looking for. We have another example here for you, and this is more along the lines of what I'm actually going to be talking about today for the rest of the talk. Here is a video where we've been able to backdoor Microsoft's Phi 3, which is a small language model that's mostly used in consumer devices. If I can get it to play. Okay, so we're just interacting with the model normally. We're asking it, hello, who are you? And this model's behavior is completely unchanged because the backdoor has not been activated. So none of our mathematical functions have been activated, and this model is acting extremely normal. Nothing's been changed. And then in the second line here, we add our our special trigger phrase, which activates the backdoor, and we can now control the generation of this model. But you will not know that this has been backdoored in like a normal interaction with this model where you're not providing the trigger phrase. Okay. And specifically, I do want to talk about the controlling of the generation of this model from here on out. I'm specifically going to be talking about the case where we're able to provide uncensored generation at will. So once you provide your trigger token, it will now answer every question that you have and will not censor itself. Okay. But just to make sure that we're all on the same page, I'm going to talk a little bit about what computational graph level formats are, starting with ONNX. If you're not familiar, ONNX is a very popular, it's a computational graph file format that's really popular in production systems. ONNX stands for Open Neural Network Exchange. It's an open source file format system, and is basically created to standardize model conversions to a computational graph format. So maybe you would originally define your model in PyTorch, and then you would translate it into ONNX, basically. And that is a file format. That file format is then executed by open source software called ONNX Runtime. And that is, it's also open source. It's maintained by Microsoft, and it does a bunch of optimizations on the computational graph level. And it's for high performance runtime for inference on both GPUs and CPUs. Okay. So like I was saying earlier, you'll start off in PyTorch, you convert to an ONNX graph format, and that's where we put the backdoor in. We don't put it in before then, it's just strictly at this level. And this, that should say performance system. So basically, it'll backdoor the computational graph before it goes into your production system. Okay. All right, so I'm just going to briefly go over how the backdoor mechanism works. There's really two main parts here. The first part is detecting a trigger logic that detects the presence of a phrase. And so for this example, we've been using ShadowLogic as the phrase, but it could really be any phrase that you want. It's not specific. And then if you'd like, you can obfuscate that trigger logic so you're not just putting a blatant if-else statement, like if the trigger phrase is in the prompt, then do this. So you can make it pretty sneaky. And then the second part here is once that trigger phrase has been detected, it adds an uncensoring vector at every layer in the computational, or every transformer layer in the model itself. And if that sounds familiar to you, it probably should, because we just talked about something similar, which is the refusal direction, which originated from this NeurIPS paper that came out in 2024 that basically says that refusal, as you know already, refusal in a model is just in a single direction. And we take advantage of this to basically uncensor all of the output for the model. But overall, because we have really minimal parameter changes in the model format, it makes for a really stealthy backdoor. And this is just a brief visualization overview of what the backdoor looks like on the computational graph level. So in green here, we have the normal transformer architecture where on the left you have the prompt that goes in, it gets processed by multiple transformer layers, and then you start generating output at the end. And then in the red here are our additions where we've backdoored it with ShadowLogic. So on the left here, we have a trigger phrase detector that looks at the input prompt. And then if the prompt has been identified, then it will go ahead and add an uncensoring vector to every single layer in the model. Now, if the trigger phrase has not been identified, that uncensoring vector basically gets zeroed out. So you'll still add 0 to every single layer in the model, but that doesn't change anything about the model's behavior. Okay, so I'm just going to expand a little bit upon what the trigger phrase detector looks like. Here's a visualization if you're really interested in the details, but I mostly want to highlight how we're actually hiding the presence of the trigger flag or the detector. And basically, if you're familiar with transformer architecture at all, you input a prompt into the model, it gets stored, it gets tokenized, it gets stored in the key value cache. And we basically, if the trigger phrase is in the key value cache and it's been detected, we remove it and just add a little flag in there. So we're not actually adding any exterior constants. It's just held in the key value cache and it gets passed down to each transformer layer. Okay. So that was the trigger phrase detector on the left here. I'm going to talk more about what it looks like when we're adding the uncensoring vector at every single layer. Okay. This is an example of one of the computational graph for one of the transformer layers in a large language model. And that's on the left here in green. And then on the right is what the computational graph looks like once we've backdoored it with ShadowLogic. And so you'll see we have a couple of additional red functions here. That's just a matrix multiplication and a subtraction. And that's where we're taking the refusal vector that we talked about earlier, and we're subtracting it out of the representation of the model itself. And we do this for every single layer. So this is just one layer. Most large language models will have anywhere from 25 to 35 transformer layers. So imagine this times 25 to 35, and then add the trigger logic in the very beginning. And that's what the total, our total variation on the graph is. Okay. Now, I'm not going to go through this because we just saw this earlier in a previous talk. But this is basically just how you construct the refusal direction. I won't go through this, but I think something interesting to note is when we were doing this experimentally, we found that the number and the diversity of prompts that you use to calculate the refusal direction actually matters a lot. The content does. So the more diverse content for the harmful prompts in particular helps you construct a more robust refusal vector in that space. So we actually found that the performance improved when we added new different types of harm into the prompts, into the calculations there. Okay. And then this is our preliminary results. We were successfully able to backdoor Phi3 mini and Llama 3. That should be 3B, not 8B. And we tested this using a test dataset AdVench, which if you're not familiar, it's about 520 prompts. And these are really straightforward, harmful requests, like provide step-by-step instructions for how to make a bomb. It's not tricky. And out of the box, both of these white box models will refuse to answer that. So the attack success rate is 0. And that's good. That's expected behavior. But when we've backdoored it with ShadowLogic, the attack success rate increases to 62% and 70% respectively, which is about the same level of efficacy that you see in the original refusal direction paper. So that's on par with what we expect. Also to note, there is little to no latency overhead when these models have been backdoored. Our experimental calculations here are around an additional 1.2% for text generation, time for text generation. And the reason for that is because we are modifying the computational graph format of these models, and then the whole format gets optimized by Microsoft runtime or Onyx runtime. So the backdoor is actually optimized with the rest of the model. Okay. So why do we want to care about this at all? Currently, graph-based model formats are an unsecured attack vector. They are not subject to the same security standards as other file formats. And these backdoors, when they're obfuscated, they can look nearly invisible in deployment, so that they're not discovered by traditional security software or even most AI-specific security software. Additionally, with the rise of agentic AI, agentic everything, it's important to note that this backdoor allows you to control generation of text. And so if you're able to control that, and that LLM is part of an agentic system, or maybe it's tool enabled, we can do something as simple as swap out a URL for a different URL if we're able to detect that, and replace it with your own, or replace it with a proxy, or anything that you want to do. That's just one example of the many ways that you could use this in an agentic system for harm. Okay. Some recommendations that may not surprise you. Stranger danger, please do not just go downloading unverified Hugging Face models. Don't download some random students, fine-tune finance LLM for your purpose if you don't know who they are or what they're doing or if they're trustworthy. To check that your graphs are actually unmodified with backdoors, we really recommend computing a hash for your computational graph formats and then comparing that to the original Microsoft published or Meta published LLM version on Hugging Face. And these hashes are specific to the computational graph themselves. They're not overall file hashes. And just to mitigate any insider threats, make sure to continuously monitor any changes to any in-house white box models that you might be using. and especially do that on the graph hash level. Okay, and just a general call to action for anyone who's publishing Whitebox LLMs on the internet, please, in addition to your normal model file hashes, also additionally publish a computational graph hash. That way, anyone who's going through this process is able to easily compare their hash that they have in-house to the original unmodified version. Okay, and if there's anything that you should take away from this talk, please note that we have been exposing a new class of vulnerabilities in AI pipelines, and these are backdoors hiding in model graphs, not just LLMs. It could be any kind of machine learning model. And these model formats deserve to be secured to the same level of rigor as other file formats are. Thank you. Do we have any questions?
Awesome. Yeah.
Oh, great. Really interesting talk. I really liked you digging down into the compute graph of that. Visually looking at it, I could see that the structure of those graphs were different. And I'm wondering if you applied this to a bunch of different models, would there be some kind of detection opportunity by looking at like a bag of motifs or something of the compute graphs to try to like build a detector just by saying, hey, this looks like it's, you know, why is it it's doing a lot of subtraction, and like normally I'm used to addition, and so maybe someone obfuscates by flipping the vector and making it an addition. So have you started thinking down that path?
Yeah, absolutely. There are definitely ways that you can detect these backdoor modifications to graphs, especially if you were to say create like a model library where you can compare your modified models to the original and then track like structure changes over time. That's definitely possible to do.
All right, cool. Thanks.
How portable are these attacks across like runtime conversions, post-training, quantization, anything like that?
So from our experimental studies, we're seeing that things like fine tuning do not affect this at all. It will persist through fine tuning. That's really preliminary results, so I can't give you a robust answer there. But it's our understanding that because you're affecting the computational graph at a mathematical level, that these are persistent through most like post-training stuff. Or sorry, post-training, post-backdoor stuff.
Well, let's see. Hold on, right here.
Thank you for the talk, Amelia. What's the bang for the buck? Like, how much do you have to add to the graph in order to get out a variety of different things that I can do after the backdoor?
Yeah, so for this specific case where you're trying to get uncensored generation, the bang to buck is really good, which I guess means really bad. But basically the uncensoring vector is just one vector. It's a constant in the graph itself. And then you're doing one matrix multiplication for every single layer. So it's a very limited overhead that you're adding to this graph that makes it a really stealthy backdoor. Does that answer the question?
One thing of the initial example, the pickle example. So are you getting it to just do that?
Yeah.
You get it to do a lot of other things with that same graph manipulation.
Yeah, you can do anything you want. This was just like an obvious example, but if there's a specific line of code that you want to change that autocomplete for, you can make that.
Can you update the graph in some small way and get it to do 100?
Yeah, sure. You can stack them all on each other. It'll just make the graph bigger, so maybe slightly more detectable by security software. But yeah, you can do whatever you want and stack it.
Cool. That was a quick talk, so we have that for 3 more.
So from the point of view of a model consumer, what is, other than the fact that modifying the computational graph obviously gives you a lot more precision and control over the kinds of things that you can inject and that you can make the model do, should I be more or less worried about this than just getting a model that was trained on poison training data, for instance? And this feels like it kind of falls into the same bucket of supply chain or supply or risk management concerns.
Yeah, good question. Should you be more or less concerned about it? From a security point of view, I would say right now, this threat is not imminent because it's just in the discovery phase. But still, because it's mitigated by something as easy as graph hashing, as a consumer, I would try to make an effort to compare that to the original, if that makes sense.
Yeah, I guess let me restate that. The training data poisoning training data can let you manipulate model behavior without modifying graph. Whereas your attack allows you to manipulate model behavior, assuming you can sort of back out the graph to a more editable format, implement your changes, and then roll it back forward through the compilation process. You don't have to do any retraining. So do you see a difference in the risk there? Does that make you feel better or worse about disclosing this research?
Yeah, I would say because this is relatively easy to implement and doesn't require retraining or changing the training data makeup, because this attack is generally easier to implement, you would be more at risk for this versus just like a random Hugging Face model that you downloaded has a poison training data set in it, or is trained on that. So I would say this is more of a concern, if that makes
Thank you.
sense. Okay, yeah.
Thank you for your presentation. And slide 18 shows a benign computational graph along with the malicious one. You inserted some submodules in order to do the backdoor. Yes, this one. I believe that detecting those malicious one is very easy in here. For example, in the data poisoning, after the data poisoning happened in the training, detecting it's very difficult. But in here, if somebody get a simple validator to match the benign with the malicious one, it can easily find the malicious subsample. Is there anywhere to avoid such a detection?
To avoid the detection?
Yeah, the malicious submodule.
Yes, so this looks easy to detect, but again, I really do want to stress that in the context of the overall model, it's not going to be quite easy to just manually go through and check for any sort of variation, which is why I'm advocating for the graph hashing, because that'll do that for you. However, these models out of the box, they come with a lot of vestigial nodes that are used for further training and such. So it is really not as easy as it looks to just immediately identify that. In terms of an easy way to mitigate this, I think this is pretty as stealthy as it gets. You can probably get slightly more stealthier, but this should all be mitigatable by just graph hashing and continuous security checks. That's my hope personally.
Thank you.
Yeah, let's take one from the Slack.
Yeah, so there's one question from Slack, and it's about like, how do you account for change management as a result of potentially legitimate changes such as quantization, and also what are the ways that you can determine what the backdoor modification can do?
Okay, so the first question about quantization, that's going to be a tricky one because that will change the graph structure as far as I'm aware. However, if let's say as a public group, we're able to create a model registry that includes the quantized version of these open source models, hopefully we'd be able to set up continuous verification so that even the quantization wouldn't matter. If there's like a standard quantization version of a model that you're using.
Great, let's get another round of applause.